Hey everyone, and welcome back to PrepFusion. So today we will be studying the last lecture, that is the lecture 14 of some time domain analysis, right? So in this lecture, basically what we will do, we'll totally summarize the whole chapter, okay, to explain you like what things are important and what things aren't, right? Even a few things if you couldn't understand, then that is okay, that is totally fine, right? What is the main thing? Main thing is solving questions. So we will summarize the whole chapter and I will tell you what things to keep in mind and what things you can also skip. But obviously if you understand, then don't skip. But if you don't understand, then you don't have to worry. Sometimes what happens is, even though I explained fully, right, it may not come to your head at that point of time. After a while, after studying a few more concepts and all those things, that particular concept will get cleared. So it happens over time, it doesn't happen at that instant only, okay? So yeah, just keep studying and keep watching these lectures and you will slowly understand all the concepts, okay? So let's start the summary. So starting the summary with basic theory points, basically now, right, I wrote all these points at the starting of this chapter, and now I think you will understand all of these points. What do I mean, what I meant by them when I wrote them, right, at that point. So what is the first point? The time response of a control system is a combination of both transient and steady state. We got it, right? Why transient? Initially, like in for a second order, we know, right, step response, what do you see? We see a oscillations for underdamped, then it dies down, right? So that is transient, right? For a critical damped, what happens? It suddenly goes like this and then it settles, right? So this part is the transient and this part is the steady state part, okay? So yeah, that was the meaning of this statement. For a first order system also you can understand. Now the transient part of the time response reveals the nature of response, basically whether it will be oscillatory or nature of damping. Basically for second order, right, whether it will be always oscillatory or oscillatory also, this is correct, how much it will oscillate and how much it will not oscillate, basically how much I can stop the oscillations. For critical damped system, no oscillations. For underdamped, there are few oscillations, then it dies down, right? So yeah, that is what basically the transient part reveals, right? It reveals. Now the steady state part of the time response reveals the accuracy of steady state error of a control system. So when we studied the steady state error, there what we did, we basically were interested in the final value, right? Not during the transient part, we were interested in the steady state value. That's why like the steady state part reveals about the accuracy of the system, right? How much accurate is the system in tracking our reference input, okay? But here there is also another thing, that for unity and non-unity feedback, that we will understand, right, in the towards the ending, okay? So yeah, this was this. Now the steady state response depends on the type of control system, okay? So the steady state response depends on the type of control system. So if it is a type 1 control system, then how will my error be? If it is a type 0 control system, how will my error be? Also the steady state error also depends on the steady state response is correct, but the steady state error also depends on the what? Also depends on the order of the input, right? So that is for the steady state error. But the steady state error response basically will depend on the type of the system, right? What type is my system, whether it is type 0 or type 1, okay? By type, we know it is the number of poles at the origin in the open loop transfer function, okay? So yeah, this is what basically my steady state response means. So I hope you got that point. Now like another thing is impulse response describes the transient behavior of the system. We did few impulse response, right? I will also do few impulse response here also. What we saw, whatever we got at the impulse response, let's say for example, for a underdamped system, for a second order underdamped system, I plotted the impulse response, right? Then what I did, I plot the step response. What do I see? Basically the impulse response was between this 0, right? It was oscillating, right? It was oscillating, okay? But when I plotted my step response, what happened? It happened that during the transient it was oscillating, then it reached to steady state. So this oscillatory part is basically the impulse response part, okay? That is why the impulse response describes the system transient behavior of the the transient behavior of the system. Now in a stable system, the transient must die out, okay? That's why the impulse response must go to 0 at t equals to infinity, okay? Or let me write this, that for a stable system, my impulse response should be absolutely integrable, okay? Impulse response should be absolutely integrable. Okay, so my impulse response is absolutely integrable. Then like what is the equation for that? How do we say that mathematically? So mathematically, right, this is IR dt, okay, and this is 0 to infinity equals to 0, and sorry, this is not simple brackets, this will be straight brackets, right? Okay, so yeah, this is what my absolute integral means. If this condition is not equal to 0, sorry, I'm sorry, I mean this is less than infinity, right? It should be absolutely summable, basically absolutely integrable, then my system will be stable, right? Then my system will be stable. Okay, so this is one thing. And what was the another thing? Another thing was basically the trick that we use, basically that my impulse response, the integration of impulse response is equals to my step response. Okay, just wait for the sound. Okay, just wait for the sound. Yeah, sorry for the interruption. Actually some few people played very loud music, that's why I had to stop the recording. Okay, now let's yeah, this was that I was writing that my step response is equals to impulse response, integration of the impulse response, right? So that's how we derive the step response, right, from the impulse response. So these were few responses for first order system. I hope you remember it. So for impulse signal for a first order system, what is happening? I'm getting a exponential, decaying exponential, right? And this exponential is dying out. So what does this represent? This represents that my system is stable. Okay, this represents my system is stable, right? Okay, and now what do I have here? I have a unit step input, and due to a unit step input, what I am getting? I am getting again exponential, right? Exponential. And what does this represent? This represents the impulse response, basically. So here I have transient, it is going from one steady state to another steady state, and then it is dying down, and then it is reaching steady state, right? Stable basically. So yeah, this is how my step response and my impulse response looks like. So if you integrate this one, you will get this one, right? So yeah, and we also did the ramp response. I hope you remember, right, all these things. I hope these you are able to recall, right? So this session is mainly for recalling things that we learned over the past few days. Okay, so this is the ramp response, basically. Now for a ramp response, what you saw, obviously my input is not bounded, so my output will not also be bounded. Here my input is bounded, so my output is also bounded. My input is bounded, so my output is also bounded, right? But here obviously my input itself isn't bounded, so how can my output be bounded? Okay, so this is not bounded, but the error here is constant, which is equal to top. Okay, we have studied all this, right? Now for parabolic input, what we did, basically for parabolic input, I didn't plot it, because why? It was of no use, because the error was also blowing up, right? It was blowing up, and the error was also going to infinity. That's why we didn't plot for parabolic input, right? So here, right, I did steady state error for a few. Okay, so I hope I haven't wrote down the formula. I will write the formula at the when we will go to steady state error part, right? I haven't wrote down the formula for steady state error. Okay, so when I had an impulse input, the output expression was like this. Don't need to remember this, just know the waveform. Okay, remembering graphs is much easier than equations, right? So some graphs you can directly write the equation. Okay, if you remember, impulse response had some decaying exponential. Okay, then for first order, so yeah, I remember that. Then what will happen? Like the step response will be some exponential, then it will reach steady state. Okay, so like that you remember, like from graphs. Or this is basic, right? First order system is simple RC. So simple RC you can relate with simple RC, and there you can derive all this, right? So yeah, this is the step input, and this is the ramp response, right? Ramp response. And what is this? This is the steady state error, ESS, right? This is a steady state error. Okay, now this is t square by 2 into u of t. Okay, so this is a parabolic input, basically, and here the error is infinity, and these are the expressions. So expressions I'm not that much bothered about, because this doesn't come, right? This is just for derivation part and for understanding part. Okay, quotients you have to derive it by yourself, okay, using Laplace and all those things. So these are not that, expressions are not that important, but these are important to keep in mind. What is the error here? What is the error here? And we don't define the error for impulse response. Okay, why? Because we just apply the input and just take it away. I am not measuring it constantly. My output isn't constantly tracking the input, right? Okay, output isn't constantly tracking the input. So what's the point even of that? So I'm not even giving any input. So if I'm not given any input, then what is the point of finding error? Okay, because there is no input, right? So what is the point of finding error? So that is why we don't use the error term for a impulse response. Okay, then we did the another variation of first order system. So this was the basic variation, that first order system with only one parameter, that is a time constant, right? Time constant is the only parameter. Then we added a DC gain and time delay. Then how will the response change? Now you tell me, how will the response change? The response will be same only, but what will happen different? Response will be scaled in magnitude and it will be delayed, right? That will be the only difference. So my response will be, what is happening to my handwriting, will be scaled in magnitude and delayed in time domain. Okay, why is this possible? Why is it simply like this? Because as my system is LTI, if my system wasn't LTI, then I wouldn't have been able to do this. So as my system is LTI, okay, so what is LTI? Remember what is LTI? LTI is linear time invariant, right? It follows the property of linearity and time invariancy. So these things have been taught in basics. So like next topic I want to come is to the effect of zeros. So what happens if I place a 0, right? So if I place a 0, the dominance of the pole nearest to the 0 reduces. So the dominance of this pole, right, will reduce. How? If this 0 wasn't here, I would have simply applied blindly dominant pole approximation and I would have got my answer. But if a 0 is here, then this 0 will reduce the dominance, right? So it will reduce the dominance, and if it 0 goes too much closer to this -1, what will happen? This will basically cancel the 0, right? There will be pole 0 cancellation. This will cancel the effect of pole. So what are the two things that my 0 does? 0 basically reduces the dominance of nearest pole and what is another thing? It cancels the effect of the nearest pole. If my 0 is exactly at that pole, right, it or I can say not cancels, minimizes the effect of pole. So with the help of 0, I can basically cancel the effect of a pole, right? Basically I can say pole 0 cancellation. Okay, I can say pole 0 cancellation. So graphically also I have done an example, and from there we understand this is the system without 0 and this is the system with 0. Magnitude I have plotted, and I can see with 0 there are two transient terms, right? Two transient terms. Okay, so here this is so higher than this one, right? This doesn't even affect this one, but here these two are close. Okay, hence I have to take in account of both of them, right? That's why. So the dominance has been reduced due to addition of a 0. Okay, so here I should write has been reduced due to addition of a 0. Okay, so dominance has been reduced. Now what happens if I place a right hand 0? If I place a right hand 0, then the sign direction of my response will change. Okay, so like these were the few points about zeros, right? So this was the last point that I told you back then. So if I add right hand side zeros, then the direction of response will change and the system will become minimum phase system, right? Direction response will change. Okay, so yeah, this was it for zeros. Now let's straight away go to the second order system, right? So this was my basic block diagram of second order system. Now what is my transfer function for this one? So like this is my standard block diagram. So transfer function for this one was omega n square by s square plus 2 zeta omega ns plus omega n square. Okay, this is my transfer function, right? So here like this is the standard one. I hope you remember this one. This is nothing to forget, right? So here I had two cases, right? I told you two cases. My system will be stable if my zeta is greater than 0 and my omega n is also greater than 0. My system will be stable then. Okay, so I will write stable system. Stable system. Okay, now my system will not be stable if my zeta is less than 0 and okay, let me write this in different color. If my zeta is less than 0 and omega n is greater than 0, so it will be unstable, basically unstable, it will be unstable. Okay, so yeah, but I'm not talking about omega less than 0 because that is like we don't use negative frequency, that's why. But if mathematically omega n less than 0 and zeta less than 0, both of them occur, then also my system will be stable. But that is not a real life case, right? Practical case. So yeah, these were the two cases that I wanted to tell you, right? Next, if my transfer function has DC gain k and a delay of dt, what will happen to my response? Basically what will happen to my transfer function? So transfer function will look like this one, right? It will get changed slightly. It will have k omega n square, okay, s square 2 zeta omega ns plus omega n square. Okay, now this is not a standard format. Also there will be delay, right? This will be e raised to power minus std. So this is not standard format, right? Not standard format. Okay, not standard form. But I gave you a few questions, right? And in those questions they were not standard, so it may so happen my transfer function isn't in standard form. So what you do, you convert that into standard form, then you solve, right? Then you solve. So my transfer function is basically my transfer function will be a function of all of these things, so you have to take care of all of these things, right? So most of the times this delay is 0 and this k equals to 1, DC gain is 1, but it may so happen my DC gain isn't 1, right? So just be careful of all those things. So my transfer function is a function of lot of things, zeta and td. Okay, so yeah, it is function of lot of things. So just be careful and about the non-standard things and how to identify standard. This coefficient of s square will be 1 always. Okay, and then these terms are okay, these terms are okay. You will what you will do, you will cramp the all s terms commonly and you will also cramp the all constant terms other way, right? So then you will compare 2 zeta omega n and you will compare omega n square with the constant terms and 2 zeta omega n with the coefficient of s. Okay, that's how we did it, right? So I hope you understood. Now next we studied about the complex frequency, so you don't have to worry about the complex frequency if you didn't understand, because it has nothing to understand. Actually it is just a frequency, okay, to basically define all the sinusoids, okay, all the sinusoids. But it is not that important. Just if you people were confused about sigma and j omega, what do they actually mean, that was for it. So that will not come in exam, that will not come in exam. So complex frequency, it not important. So complex frequency, only it was only for knowledge purpose, right? Not for gate purpose. Obviously, like it may help you in gate exam, it may help you, right? Because all the knowledge that you get, it helps somewhere or another, right? But it is not that important for gate purpose. Okay, at least in control system. Okay, in other subject it may be important, but at least in control system we don't know. Okay, so now let's come to the oscillations part. So I was plotting the responses and I saw few oscillations, but what does oscillations mean? Basically oscillations mean, tell me, it is a movement around the steady state point, right? So my, for under time system, it was my steady state point and it was oscillating, right? So it is the movement around the steady state point. Okay, movement around the steady state point. Now what is damping? Damping is basically an influence to the system to reduce or prevent my oscillations. Okay, that is why we use damping, right? So I don't want too many oscillations. Why? Like let's say you have an automatic car, right? You have an automatic car. Now like in the US, obviously not in India. So you're driving your car, you are not driving, you're just sitting in the car and you are in the middle lane, right? You are in the middle lane. Okay, now if the car system is oscillatory, what will happen? It will just oscillate in the lane, right? It will just oscillate in the lane and some accident may happen. That's why you may not want too much oscillations, but also you do not want too much of damping also, because that will just slow down your response, as we saw in overdamp. Okay, we'll come to that as we saw in overdamp, right? So that is the data basically. So yeah, damping. What is damping? Damping is used to reduce, like it is an influence in the system. Okay, reduce or prevent oscillations, basically prevent oscillation, right? Okay, so this is basically what damping is. Now what is my damping factor? Basically, what is my damping factor? So this is the next point. Basically, damping factor is the, it tells us about the amount of damping present in the system. So amount of damping in the system. What about the natural frequency oscillation? So natural frequency of oscillation, right? It is the frequency at which my system oscillates if there is a small disturbance present initially. Then I took off the disturbance, right? Then the frequency at which my system oscillates, it will be a natural frequency oscillation. And when my, without any damping, when no damping is present. Okay, that is also another thing. Okay, when no damping is present. So should I write the definitions? Yeah, I have to. So frequency at which my system oscillates some disturbance initially. Okay, so this is basically what my frequency of oscillation without the presence of damping. Okay, without the presence of damping. Now, what is my damped frequency of oscillation? It is basically the frequency at which my system oscillates in the influence of damping. Here there was no influence of damping, but here there will be some damping present. So frequency at which my system oscillates in the influence of damping. In the influence of damping. So this is what this damping factor is. What this is known as the zeta, right? And this is known as the omega n, natural frequency, oscillation frequency, and this is known as the omega d. Okay, so yeah, and I directly come to that impulse response, right? So this was the basically what do you say, I haven't written it down. So this was the second order system standard, and the impulse response, not this one, right? And the impulse response for all of them, I have like drawn a circle, right, and told you like how to remember this. So here, what was the system here? This system was critical damp, right? As you can see, okay, this reaches and then goes down. Okay, so no oscillation present. So this is basically critically damped. And what was this system? The poles. So here, if my system is critically damped, then what do we know about the poles? The poles are equal, negative, okay, and present over here, repeated negative poles, right? And if my system is underdamped, then what can I tell about the poles? The poles are lying on the left hand side of this plane, and they are complex conjugate of each other. So here, this is the overdamped system, okay, overdamped. And let me, what about here? What do you say here, right? This is the, what does this mean? This means my zeta is more than 1, hence my system is sorry, this is underdamped, sorry, I showed it overdamped, sorry, underdamped, okay. And here this is overdamped, right? What do you know about the poles of overdamped? So one pole will be very nearer to the origin, and another one will be very far, right? Very far. Hence we can apply the dominant pole approximation. Basically, it basically is a first order system only, right? It works like a first order system only. Okay. So, and what is this? This is the undamped nature. What can I tell about the poles of undamped? The poles are lying on the imaginary axis and are conjugate of each other. Imaginary conjugate, right? They lie on the imaginary axis. Okay. So, and this is, what is this? Like this is a circle which is omega n square, right? And here in the imaginary axis it becomes omega n only. So the poles will be j plus minus j omega n, and omega n is the natural frequency of oscillation. So if here, what does this represent? No damping is present. That's why zeta is 0, right? No damping is present. Hence why it oscillates in the natural frequency of the system. And on poles lying on the right hand side basically are the unstable ones, right? Unstable ones. So this represents the negative zeta overdamped. It goes like this one. This is negative zeta critical damped, and this is negative zeta underdamped. So like names, I have just put them. Names are not standard, okay? Whatever I felt like these are good names, I put. But what is the main thing here to notice? Main thing is these are unstable. These are all unstable, and these are almost similar to this this one only, okay? Almost similar, but like opposite man, right? This is oscillating and it is dying down. Here oscillatings are regenerating, right? Getting more energy, so they are blowing up. Okay, here it is blowing up, right? So yeah, and this is marginally stable, right? So also I have told you all those things about the roots, about the zeta for underdamped is between 0 to 1, and zeta for critically damped is 1, zeta for overdamped is greater than 1, right? And for undamped is 0. Why, you can understand, right? It depends on the damping. So damping is related with the zeta obviously, and here like the oscillations don't decay. Here the oscillations decay, and here also obviously there are no oscillations present. This is the ideal system that we want, right? No oscillations and fastest response. So this is the ideal system. And here what is this overdamped? Here also no oscillations present, but this causes delay in the system. I mean, this reaches steady state at a slower rate than this critically damped system. Okay, so yeah, these were basically for the overdamped, underdamped, all those things. Okay, so I have put a summary, I think, here. Yeah, So you can go through the summary. Basically I told everything that basically I wrote everything that I told you, right? Why did I told you first? So that you can also get this in your brain. Just by reading this is not okay, right? Not okay. You should work with me, right? You should work with me. You should think in your mind what am I saying before, like you should answer in your mind what I am going to say, okay? So that is important. So that's how your brain will work, okay? So I have wrote down the pole locations, all these things, right? So you can see from here, I will not explain, I have already explained. So this is for the stable system where my zeta is greater than equals to 0. Stable when zeta is greater than 0, marginally stable when zeta is equals to 0, okay? So now what we will do, we'll like do the summary for zeta less than 0. So it will be always unstable because my poles will lie on the right hand side of the S-plane. So poles lie on the right hand side, the poles will look something like this and system will be always unstable, right? So now we will come to another important point. After this we taught we learned was that angle of inclination. So what is my angle of inclination basically? So for angle of inclination, let me draw the graph, right, and put a pole location, right? And this is for underdamped system only, but this can work for few other systems also, few other types of damping also, okay? But this won't work for a overdamp, right? Overdamp it won't work. This is j omega d, this is minus zeta omega n, and this is basically my pole location. What is this distance called? This distance is omega n, right? This distance is omega n, and this height is, what is this height? This height is omega d, and obviously this length we know is zeta omega n, right? This length is zeta omega n. So yeah, let me reduce the size. This is like a, what do you say, giant in front of this one. So this height is zeta omega n, right? Okay, I understand. So yeah, now simply what is angle of inclination? Angle of inclination is not like my coordinate axis angle. So what was coordinate axis angle? This was taken from this, right? Positive x-axis, right? We used to took it from this one, but angle of inclination is different. This is for control system. So here my angle of inclination, as I always lie on the left hand side of the S-plane, I start from negative x-axis, right? I start from negative x-axis, then I go towards the positive, basically in the positive what do you say, imaginary side, right? So here I will measure my angle of inclination. So my angle of inclination for this case will be let me take another pen, will be this one, theta, right? Okay, this will be my angle of inclination. So basically I will write all the terms related to theta, sine theta and zeta, right? So that you can recall all these things. So firstly, what is my omega d defined as? Omega d can also be written omega d, I can write also what was the formula for omega d? It was omega n under root 1 minus zeta square. Now this is for a underdamped system only. So this is for underdamped system, right? Now what is my basically like zeta omega n is zeta omega n only, so that is not defined. So from here I can write different trigonometric equations, right? So first one is what? Tan theta. So what is tan theta? Tan theta is basically height upon base, right? So it is omega d upon zeta omega n. So omega d upon zeta omega n. So what is this equals to? This is equals to simply omega n will get cancelled. I will get under root 1 minus zeta square by zeta, right? Omega n will get cancelled. Now I can write cot theta, the inverse of this one, right? Cot theta equals to zeta by under root 1 minus zeta square. So this is the very important relation that I used in finding the MP, right? Maximum peak overshoot. Now what is my, similarly I can derive cos theta, sin theta, all these things. So what is my sin theta? Sin theta is basically height upon base, right? So it is sorry what I'm talking, yeah, height upon hypotenuse. Okay, so opposite of this angle, right? So it is omega d by omega n. Okay, omega d by omega n. So what is this equals to? So omega d is basically equals to omega n under root 1 minus zeta square divided by omega n, right? So what do I get? I get 1 minus zeta square. So sine theta is, I can write like 1 minus zeta square. Now what else can I write? I can write cos theta, right? Cos theta, what is cos theta equals to? Cos theta simply equals to zeta omega n by omega n, right? Zeta. So what is my theta equals to? Theta equals to cos inverse zeta, right? So I can find my theta from here, or I can find my zeta from the angle of inclination, right? So both of these are very, very important. Both of these are very, very important. So this is my zeta and theta. Now, like, what are the things to keep in mind? So what was the range for theta for my system to be stable? For my system to be stable, theta should lie between 0 to 90, right? In the left half, right? Left half here. Okay, that is one thing. Now if my theta is equals to 0, what does that mean? That means my system is undamped, right? So this is the edge case, and this is for undamped system, and this is for, what was this for? This was for the critical damped, right? If my theta equals to 90, then zeta becomes 1. That's why this was for critical damped. Okay, now if my theta is more than 90, what happens? Okay, sorry, I did one thing wrong. Sorry. So it was opposite of this one. Okay, sorry. Like theta equals to 90 was for here, okay, and theta equals 0 for here. So because it's cos 0, right? So here, right, if my theta is 0 degree, it is lying over here, and here what happens? The roots become repeated. So this is critical damped, and if my theta goes to 90, so my roots are at imaginary axis. So this is the location of root, right? The roots are at imaginary axis, okay. Then it will be undamped, right? It will be undamped. So it will be undamped at 90, and it will be critical damped at 0 degree, okay. So this theta, right, is basically the direction of the roots, right? Angle of the roots from the actual point, from the negative x-axis. That's how also you can say about the angle of inclination. So this is basically my 0 to 90, and for this range, right, my system is stable. System stable. Now if my theta is more than 90 degrees, what happens? If my theta lies between this range 180 degrees, what does that mean? So this is going beyond here, right, beyond this axis. So if my roots lie in this range, what does that mean? That means my system is unstable. It is basically roots are on the right hand side of the S-plane. So system will be So yeah, let's go to the summary of damping in RLC circuits. So in RLC circuits, we have two types, right? One is series RLC, one is parallel RLC. So like what I can say is, basically these are all the cases, but you don't have to remember all this. Just remember what was the formula for zeta. So what was the formula for zeta? Zeta for series RLC, right? Series RLC. What was it equals to? It was equal to simply R by 2 under root L by C, not L by C, sorry. How you used to remember this? C by L. I told you, right? What is the unit of L by C? Under root L by C. It is the impedance, right? It is basically known as also the characteristics impedance. This electrical people will also study, and the electronics people will also study. In EFT, electronics people will study, and in power system, electrical people will study. Under root L by C. Very, very important term, right? So this is the unit of resistance, I mean basically impedance, and this is also ohms, right? So that's how this will get cancelled, and that's why my zeta is dimensionless. So from here I can basically cross verify whether I am writing the formula correct or not. Okay, so this was one formula. Now what was the zeta for my parallel RLC? What was the zeta? It was basically the opposite, right? It was basically 2 by R under root L by C. Okay, basically if you know one of the zetas, then you will be able to know the other zeta, right? So this was basically my, okay, sorry, one thing I wrote wrong is zeta parallel is basically this one, right? It should be 1 by, sorry, 1 by 2, right? 1 by 2 or under root L by C. Okay, so this will be for my parallel zeta. Now if you forget this one relation, like one relation you can remember through the quality factor is, my quality factor will always be 1 by 2 zeta, right? So my quality factor will always be equals to 1 by 2 zeta. So this you can remember always. So these three formulas are important. Okay, so like for series RLC, parallel RLC, these three formulas you remember and you are good to go, right? Good to go. Okay, obviously in the resonance chapter, quality factor is of another importance, and obviously you study much more different things there. So yeah, but for control system or for damping purpose, like if you remember these two formulas, right, and from here you can derive any condition. Okay, any condition. This is just a summary. Okay, just to show you like how I derived all those things, just to recall you. Okay, but these are the three formulas that you need to keep in mind. Okay, so yeah, this was for the zeta one. Now let's go for the next topic, that is the step response of undamped system. So the step response, right, here I have taken a generalized case where this A, right, A is the amplitude of the step, amplitude of step, and what is this K, and this K, right, K is the basically the DC gain, right, DC gain of the system, DC gain of system. And this is very important formula, you have to remember this. I'm sorry, you have to remember this, right? So this may come in exam or something, so you have to remember this no matter what. And this is like a very used formula. So underdamped system is very used. Okay, so because achieving critical damped system is difficult, and obviously overdamped we don't want, and obviously undamped is marginally stable, so only we are left with underdamped, right? But we have to vary the zeta so that I can get a desired system, right? So this was the equation, and these were the responses for a step response, right? So this was for the underdamped case. Okay, and this was for all of the case. So this was for oscillating always for undamped. Now this is oscillations are dying down. Okay, now this is critical damp reaching fast and there are no oscillations, and this is overdamped, right, reaching very slow. Okay, and there are no oscillations. So these were few like responses. Okay, I hope you recall, and this was the table basically. This was the table, right? And this was a summary table. Okay, I won't go too much into it because the stability already we know through impulse response, but these are the responses. If my impulse response is this one, so I can see my, like this is my transient nature, and this is also my transient because it is never dying down. Basically it is never reaching steady state, right? Hence here also the step response also never reaches steady state. Here this is transient nature, and I see the transient nature and then it reaches steady state. Here my transient nature dies down, that's why this reaches steady state. This also dies down, reaches steady state. This also dies down, reaches steady state, right? So yeah, so that was basically it. Now next what we studied was the basically the performance parameters of first order system, right? So the performance parameter of first order system is basically, first one was the rise time. This was the first order system, so do keep in mind. So what was the definition of rise time? So what was it? Remember, it was going from 10% to 90%, right? So 10% to 90% of basically let's say y of infinity, right, steady state value. So what was it equals to? So my t rise equals to 2.2 tau, right? If you don't remember this one, just simply derive, because deriving the first order equation is very easy, right? Just simple exponential, right? Simple exponential, so you don't need to stress much. Okay, now what about my delay time? What about my delay time, right? What about my delay time? So what was the delay time? Delay time was from 0% to 50%. Okay, y of infinity, and What was the value for this one? So I like this is also something 0.693 tau. Okay, so if you don't remember, just derive, just write the exponential equation as I derived, right, for during the derivation, right. And what was the settling time? Now settling time has two parts. One is for 2% error band, one is for 5%. So 2% is basically 2% within the steady state value. So one is the 2% error band and one is the 5% error band. So what is the 2% error band? 2% error band is basically equals to the t settling is 4 tau, right, and for 5% error band it is lesser, right. Obviously it will take less time to reach within 5% of the steady state. Okay, that's why this is lesser. Just need to remember these two and you are good to go. Mainly this one is asked, right, 2% error band is asked, but just in case if they ask this one. But if they ask any other, you can also find that one, right, using the derivation that I did there, right. So this is for the first order system. Now let's study for the second order system. So in second order system we have to study the performance parameter of second order system. So this is the rise time basically. So what was the definition of rise time? So it is a bit different, okay, for different types of damping. For underdamped, what was the definition of rise time? It was basically the first time it reaches from 0 to 100%. So first time reaches from 0 to 100%. Okay, so what was the basically equation that we should do? What we should do was make the sine omega dtr plus theta omega dt sine omega dt plus theta equals to 0, right? Because okay, here let me, like, when will this reach 100%? When this term becomes 0, right, for the first time. So how will this term become 0? Either at infinity or if I make this one 0. So the first time how it will go to 0? Omega dt plus theta needs to go to what? Needs to go to either 0, but 0 it can't go because then my time will come out to be negative. Obviously 0 it can't go. Now the next option, what do I have? I have this one equals to pi, right? That's why that pi term came. Okay, so that's how you recall and remember the formulas, right? If you know the derivations, from there also you can understand how to remember the formulas. So basically I have to make this sine omega d tr plus theta equals to 0, right? So if I want to make this one 0, this will be equals to pi minus theta by omega d. So here you will recall that your omega d used to come in the denominator, okay, and in another time what was that like parameter omega n used to come. Okay, that is just, you have to mug that up so you can find the differences from this one and that one. So this is my t settling. Right? So yeah, now what is my peak time? Peak time is basically when it reaches the peaks, right? So here, right, here if you see, it reaches the peaks. Okay, at certain points it reaches the peaks. So these are my basically peak times, right? So mainly I will be interested in first peak, but they may ask you for the second peak, third peak also. So peak time TP is equals to my, what was it? It was n pi by omega d, right? It was n pi by omega d. So why? Because this reaches like this function, okay, goes to maximum at that point of time. That's why it becomes n pi by omega d. So yeah, we differentiated and from there we found out. Okay, this was just not any intuition, we just found it out. So now there are two cases when my n is even, right? Like first of all, when my n equals to 1, that I will write n equals to 1 is the first peak. So that is very important, right? And that is the 99% of the cases they will ask first peak, right? Now if my n is odd, right, then what I will get? I will get overshoot, okay, which is above my steady state value. That is what my overshoot means. I am shooting above my steady state value, known as the overshoot. And if my n is even, then what happens? Then I am at the undershoot, right? I'm at the undershoot, so I'm getting minima. Okay, from the graph also you can see. So this is the first peak, then at the second, I mean n equals to 2, I'm at the minima, then again at n equals to 3, I'm at the maxima, basically for that local maxima. Basically this is local minima and local maxima. Okay, so yeah, this is basically this one. Now like what is overshoot and undershoot, like the equations basically. So overshoot and undershoot, what are the values equals to? So for this one, my y of t is, I hope you remember, is ak into 1 plus e raised to power minus pi cos theta, right? Okay, this was my equation for overshoot. But if I write it for generalized case, this becomes n pi. This becomes n pi, right? Now here my n is odd. Okay, and if I write it for basically for undershoot case, right? Undershoot, what does it become? It becomes ak 1 minus e raised to power minus n pi cos theta. Okay, and in this case my n is even. Okay, minus even. So this is basically my undershoot, right? This is basically my undershoot. Okay, so like here in the graph, can we explain the overshoot and undershoot? I've already told you in the previous graph also. So here this is n equals to 1, right? N equals to 1, this is n equals to 3. These are the overshoots. Okay, and if you see that this is n equals to like this is n equals to n equals to 4. So these are the undershoot, right? So these are the undershoot basically. So I hope you understand, these are the undershoot. And what about the settling time? Basically here, right, obviously I can't tell, like it will go above this 95% many times. I mean here what was the definition of settling time? 90%, right? So it will go above this 90% multiple times. So how will I define my settling time? It will be within the error band. Now positive and negative, right? So my error band will be something like this. This will be defined as my error band within the 90% error band, right? So this is known as the error band. Okay, so this is basically my 90% error band. Now few things what I wanted to mention was, this is oscillating, right? Oscillating, obviously not repeating exactly, but still I can see the pattern, right? Pattern, it is repeating. This is reaching peak here, then again it is reaching peak here. So what is the difference between these two? The difference between these two is what do you say, 2 pi by omega t, right? So what is my time period of oscillation? It is 2 pi by omega t. So here from here to here, one is pi by omega t. From here to here I am reaching 2 pi by omega t. So my period of oscillation will be 2 pi by omega t. So this is known as my period of oscillation, right? This is also another important parameter. And what is the other parameter? How many number of oscillations I will make in one settling time. To settle, how many number of oscillations I have to make. So basically it is denoted as n naught, and it is written as what do you say, t settling total time by time period, right? That will be my number of oscillations. So by time period. So NO equals to T settling by TO, right? T settling by TO. So basically that is my number of oscillations that I need to make before I reach my steady state, or my settling, basically before I settle to my within my error band. Okay, so yeah, that was it for the all these parameters. Now the next parameter is maximum peak overshoot. So what is basically my maximum peak overshoot? My maximum peak overshoot, right, is basically the overshoot above the steady state value. So it can happen like it is for multiple n's, right? Multiple n's, but I will only check for the maximum one, that is for the first peak overshoot. There it overshoots the maximum value, right? So my percentage MPO, what is my percentage MPO defined as? It is defined as EK. I'm writing for the generalized case, so I'm deriving it a bit also. 1 plus e raised to power minus it was pi cot theta minus ak, right, divided by ak. So we do the normalized one, we normalize this one. This is equals to ak, this is into 100%, this is into 100%. So what is this equals to? This is basically equals to e raised to power minus pi cot theta, and I can further derive it, right? I can further derive it like this into 100%, okay, and I can further derive it equals to e raised to power minus pi theta by under root 1 minus theta square, okay. So this can be further derived like this one into 100%, okay. So these are the things that you have to keep in mind, right? I'm just writing the things that you have to keep in mind. This is very, very important formula, you have to keep this in mind, okay. So this will come in exam, no worries. And like from here what I can observe, okay, I will write it directly here. If you can check it for yourself, that my MPO is inversely proportional to my zeta and my rise time, okay. Rise time was what? Rise time was this, right? This was the first order, sorry. Okay, rise time I still didn't, okay, wrote it. So rise time is basically, yeah, here, right? Rise time is here, sorry. Rise time is here. So theta, right? Theta is cos inverse zeta. So from there if you derive, okay, by wrong I wrote it settling time, I'm very sorry, okay. I was in some other mood. So this is rise time, okay. So yeah, rise time is equals to pi minus omega t. So here if you compare that, my rise time will be directly proportional to zeta, okay. So what does this mean? This means if I increase my zeta, my peak overshoot will decrease, so that is a good thing. And you can understand intuitively also, if I increase my zeta, if I reach critical damp, obviously I will have no overshoot, that is good thing. But my rise time will increase, right? My rise time will increase. So maybe I don't want my rise time to increase, maybe I want my system to start fast, okay. Maybe I want my fan to start reach to its near about its peak performance very fast, okay. Then it may oscillate a bit, then it will settle down, that is fine. But yeah, that maybe that are my requirements. So for that reason I have to find out like which design is the most suitable for me, okay. So that was basically for the relation between zeta and rise time and MPO, right? Now we had another time, that was the delay time. Again, right, these are not that much important. I mean, these are important, but you just have to mug this one up, okay. I'm sorry, you have to mug this one up. So what was this? This was basically 0% to 50% of y of infinity, okay. So the formula is like a first order approximation, which is equals to 1 plus 0.7 zeta by omega n. So you compare with the rise time, and from there you will understand. Now settling time, right? Settling time is similar to like first order only, it is 4 tau, okay. But it has again two cases. So what are the two cases? It is, one is 2% error band, another one is 5% error band, right? Another one is 5% error band. So here it is 4 tau and here it is 3 tau, right? Now tau is different for different types of damping. For underdamped my tau is different, and for overdamped my tau is different. So let's see how different they are. So here it is basically 4 upon zeta omega n, and what is this? This is 3 upon so I will write this in zoom format, 3 upon zeta omega n, okay. And what is this equals to? Okay, what is overdamped? So for overdamped, just try to remember what was the pole location. Basically it was something similar to this one only, but it was more nearer to the origin, okay. So my denominator will reduce, right? It is more nearer to the origin, that's how you can also understand. So this is 4 upon my zeta omega n, and I had a minus, so it becomes more nearer to the origin, into omega n under root omega zeta square minus 1. So you can remember like this one, right? So now this is 3 upon zeta omega n minus zeta square minus 1. Okay, so yeah, this is basically my settling time. So you can remember it like this one. Okay, so now let's understand the decay time, right? What is decay time? So decay time is basically the the decay ratio. Decay ratio is basically the second overshoot divided by the first overshoot. Okay, why? Because I'm just measuring how much it is decaying after each period, right? After each period, that is why this is known as the decay ratio. How much is it really decaying? So basically it is the ratio of MPO 2 divided by MPO 1. Okay, what is this equals to? So this is equals to e raised to power minus 3 pi cot theta divided by e raised to power minus pi cot theta. Okay, so this is my decay ratio, which is equals to e raised to power minus 2 pi cot theta. Okay, so this is basically my decay ratio. Now, like, then we studied the variations of opoles. So these are the performance parameters, and then we compared the each parameters by varying the location of the poles. Okay, how did I vary? I kept one thing constant, either I kept theta constant or omega d constant or zeta omega n constant. Then I varied the other two parameters. Okay, then I saw like there was a horizontal movement, there was a vertical movement, right, and there was a diagonal movement, right, diagonal movement. So then I compared each of them, the performance of each. Like I took 3 poles location and I compared each of them, and I saw whether my rise time is increasing, what is happening to MPO, all those things, right? So that is homework for you. You revise that one. Okay, that is important actually. So you revise that one, and from there you will understand like which system to pick, which system is best for me to pick. Okay, so that is the basic practical knowledge. Next is the very important topic, which is the steady state error, right? So yeah, sorry for the interruption, actually someone came at the door. So next what I was talking about was the most important topic, that is the steady state error, right? So for steady state error, what is the meaning of steady state error? So the definition is, the steady state error of a system is defined as the discrepancy between output and the reference input when the steady state is reached. So basically it's a steady state, and obviously for my system to reach steady state, it should be stable. So first condition is it should be stable system. Okay, it should be stable system. And this is the global definition, but first we'll understand the for unity feedback. Very easy to understand, right? Then we'll understand for non-unity feedback. Okay, so what is my E of t? This is the global definition. So this will work for unity and non-unity, because my reference input keeps on changing. Okay, in case of unity feedback, my reference input is basically the input itself. Okay, because my output directly tracks the input, so output directly compares with the input itself. Okay, and for non-unity feedback, my reference input is something different. And like this is a very controversial topic also, because people define error in different ways. So you may define error in something some other way, and I may define error in some other way. So yeah, that is also another thing. This actual output. So yeah, now like here I have drawn a block diagram, and from here you can understand the error, right? So this is the actuating error signal. That is usually what is asked, right? That is usually what is asked. So I hope you remember that in your head there was one controller. Okay, there was a controller here, there was a processor here, and there was a sensor here. So controller was actually measuring the error, okay, between the output and the reference input. Then it was sending it to the controller. So if the error is 0, it will send some fixed signal. Obviously the input to the processor will not be 0, because it has to continuously the AC example, right? It has to continuously push the air, right, cold air, so that the room stays in the steady state in the particular temperature. So obviously the input to the processor won't be 0. Okay, so yeah, that is one thing. So yeah, this is what my block diagram is. So from here you can understand what is the error meaning actually, right? So this is the formula for this one. Okay, we derived this one, so I won't again go into the details of this one. So we derived this one, and then we got the equation as this one. This is for the unity feedback. Okay, this is for valid for only unity feedback system. Unity feedback, right? So next, like we derived few steady state error equations for like step input, and for step for ramp input, for parabolic input, right? And we derived few coefficients like position error coefficient, velocity error coefficient, and my acceleration error coefficient. So what is this equals to? what is this equals? This is basically my steady state error. Okay, steady state error, and like I will write the steady state error for a type 0 system. Okay, so also I will come to type also, but let me first write the steady state error for a step input. This is 1 plus kp. So basically ESS is equals to 1 plus kp. So kp is what? Kp is my position error coefficient, which is defined as limit s tend to 0 g of s. Okay, now this is valid for a first order system because not first order, not for first order. This is valid for a type 0 system because I'm getting a finite error for a step input. And when does that happen? That happens when my system is type 0. Okay, now what was the other case? So let me color this in different. ESS is equals to 1 by a by kV, right? This is for the generalized case. So if my input is a RAM and it has amplitude of a, then my ESS will become a by kV. And what is my kV equals to? kV equals to limit s tends to 0 s g of s, right? So this is my kV equals to, and this is valid, like I'm getting a finite error for a ramp input. So what will be my type of the system? I hope you remember, right? My type and the order of the input has to be same, okay, for me to get finite input. Not the order, I mean basically what do you say, order minus 1 basically. So this will be what? This will be type 1 system, right? And now if my steady state error equals to a by ka, okay, so for this parabolic input my steady state error will be a by ka. What is this called? This is called as the acceleration error coefficient. This one was the velocity error coefficient, right? So my ka is defined as limit as s tends to 0 s square g of s, right? So like these things I hope you remember. Then I gave you a summary, okay, of all the tables, right, with the inputs and all those things. So this is not that, like this is already know type 0, this is finite for step input, okay, for type 0. For type 1 my error will be 0. So if I increase my type, my error reduces, right? It reduces, it goes to 0. But if I increase my order of the input, then again my error also increases, right? So here the error increased to infinity, here the error is finite for type 1, and again if I increase my type further, it is going to 0. For parabolic input also same, right? For type 2 this is finite, for all type 0 and type 1 this is infinite, right? So yeah, so here I have like wrote few summary points that I didn't wrote down in the lecture, right? So you can summarize from here. So if order of the input is greater than the type of the system, then the error will be infinite, okay? So if the order of the input, what is the order of the input? It is, let's say 1 by s, so order is 1, right? Order is 1. So okay, I should write order minus 1. Because order is 1, so like now if 0, if this is 0 and like let's say if this is ramp, so ramp is, what is the order of ramp? Ramp is 2, right? So order of the input is 2, but this is 2 minus 1, which is 1. So 1 is greater than the type of the system, then the error will be infinite, Now I have to write again order minus 1. Like this for understanding purpose, there is no need to mark this one up or something. I hope like this is like for the intuitive approach, right? And like if order minus 1 of the input is lesser than the type of the system, then error will be 0. Like here, right? If I am applying like this is type 1 and applying a step input, so what is order minus 1? It is 0. 0 compared to 1, so my error will be 0, okay, like that one. If the order minus 1 input is equals to the if my order minus 1 input is equals to the type of the system, then error will be finite here, right? Order minus 1 is 0 and this is type 0, so my error becomes finite, okay? And for type 0 system kp, okay, refer to dcgan. So dcgan, right? If you have some confusion, if they ask dcgan, so like kv is referred to a dcgan of oltf and this one, right? So if they ask a dcgan when there are 2 poles at the origin, then maybe they are referring to d secant of OL tape for acceleration coefficient. So yeah, that this type of question also comes. So how you might ask, how you will find d secant when there are poles at origin for like two poles at origin? How will you find? So maybe they are referring about the acceleration error coefficient. Like that you understand and you solve, right? Okay, these were few points about the steady state error for unity feedback. So yeah, that is basically end of this time domain analysis. I hope you like the summary, and like I hope you like the whole chapter, right? Like I've given you like a proper visualization and all those things, provided you with what are different types of damping and examples also, and shown you like how the damping works, right? So yeah, I hope you like the like analysis and like the teaching stuff. So if you like the teaching, so please do hit the like button. That's how I realized that yes, this is helping you guys and like you're understanding all the concepts, right? So it is very important that you like the video, and yeah, share it with your friends. And next we'll start the Routh-Hurwitz criterion, right? So yeah, thank you for watching.